The last decades of the 19th century marked the dawn of modern physics. It was the period when a new era of science emerged. Scientists discovered the world of atoms that gave a new dimension to further discoveries. Physics attained new heights and scope. 100 years ago, a French physicist, Henri Becquerel, discovered radioactivity that laid the foundation of nuclear physics, and today it is a boon for mankind in the treatment of serious diseases like cancer. Nuclear research has led to the process of identifying diseases and producing new medicines. The story of discovery of radioactivity is actually connected with the discovery of X-rays. It was in November 1895 when, while working on cathode rays, a German physicist, Wilhelm Röntgen, discovered X-rays. A report on Röntgen's discovery was presented in the weekly meeting of the Science Academy in Paris on the 20th of January 1896. In this meeting, French physicist Henri Becquerel was also present. Images of X-rays showcased there fascinated Becquerel, and he became curious to know more about those mysterious rays. Becquerel had already worked on luminous substances. Luminescent substances are of two types. One is fluorescent and the other phosphorescent. Fluorescence is an optical phenomenon in which the substance absorbs the rays in the ultraviolet range and re-emits light in the visible range with a longer wavelength, like fluorescent tubes used in our homes. The tube is lined with a coating of a fluorescent material. When ultraviolet rays are emitted in the tube, the coating of fluorescent material absorbs the UV rays and the tube re-emits fluorescent visible light. Some materials have an afterglow, that is, they appear to glow even after the light source is removed. Certain watches have dials that glow in the dark. Then, there are some glow toys for kids that exhibit this phenomenon. Becquerel had a ready source of these luminescent substances to pursue his own investigations on X-rays. Becquerel hypothesized that a material had to be fluorescent and phosphorescent to emit X-rays. To test his hypothesis, he experimented with uranium salt. He wrapped the photographic plate with black paper, placed a crystal of uranium on it, and exposed it to sunlight. After developing the plates, Becquerel found a black image of the size of uranium on the photographic plates. Becquerel thought that the crystal had absorbed the sun's rays, which was then emitted as X-rays. On the 26th of February 1896, Becquerel thought of doing this experiment again, but for many days the skies on Paris were overcast and there was no sunlight. So he kept the photographic plate wrapped with black paper and uranium crystal in the drawer of his table. At last, on the 1st of March, he thought of developing the photographic plates. He expected a faint image on the plates, but to his surprise, the image was clear and strong. Now how could this be? Uranium was still emitting radiation without an external source of energy. This was something unbelievable. He was confused. It was for the first time that a material could produce energy without being exposed to any source of energy. Becquerel thought, was he observing a long-lasting phosphorescence or maybe something else? This led him to a new path in his investigations. He melted uranium nitrate into a liquid state and then recrystallized it, which ceased the phenomenon of luminescence in it. But still, the images on the photographic plate were as strong. The results surprised him, one after the other. Seeing this, Becquerel inferred that the uranium salts were exhibiting a special property. They were emitting a new kind of radiation. Whether the salts of uranium were kept under the sun or in the dark, whether they were phosphorescent or not, they emitted rays in every case. Becquerel called those radiations uranium rays. Unknowingly, what Becquerel had discovered was radioactivity. During that period, Marie Curie was seeking a subject for her research. Curie started her research on the invisible rays of Becquerel. But Curie neither had a laboratory nor the equipment for the research. So, she transformed the godown of a university into a laboratory and started her experiments on the particles of uranium. In order to measure the electric charge of the radiations of uranium, an electrometer made by her husband Pierre Curie was used for the purpose. The machine was not too sophisticated. Pierre and his brother designed it about 15 years prior to this. Marie decided to explore other elements that could emanate radiation. She discovered that thorium also emitted such rays. And then she called this emission of invisible radiation as radioactivity, which is known by this name till today. Marie proceeded further in her investigations. She was exploring such elements other than uranium and thorium that were capable of exhibiting radioactivity. She selected the ore of pitchblende for her investigations. She separated uranium and thorium from the ore and tested the remains of the ore. The results were surprising. She inferred that the remains of the ore were significantly more radioactive than the pure material. In July 1898, she announced that the ore contained some unknown radioactive elements that were present less in quantity, but they were very powerful. After that, Pierre and Marie both began to discover the new substances in the ore. They discovered two new elements. One was named polonium and the other was radium. Radium was thus discovered but was not yet extracted. At last, on December 1898, after a struggle of 4 years, purified parts of pitchblende exhibited glowing particles. They discovered some chemical properties of radium. The whole scientific world bowed their heads in the honor of Pierre and Marie. For the discovery of radioactivity, Becquerel was awarded the Nobel Prize for Physics in 1903, which he shared with Pierre Curie and Marie Curie. Madame Curie was the first woman to receive the glorious Nobel Prize. In 1911, Marie Curie was again awarded the Nobel Prize in Chemistry for discovering polonium and radium. Curie then became the first person to get the Nobel Prize for both physics and chemistry. In the history of the Nobel Prize, Marie is associated with many glorious achievements. She is the first lady whose daughter was also awarded the Nobel Prize. Scientists considered the discovery of radioactivity a miracle that unfolded many surprising facts. Radium and other radioactive materials that were discovered had another interesting property. As they emitted energy, they got converted to these elements. Before that, scientists used to believe that the elements always exist in their original forms. Actually, all the elements are made up of atoms. An atom consists of a small nucleus. The nucleus comprises even smaller particles called protons and neutrons. The number of protons present in the nucleus of an atom is known as its atomic number. The total number of neutrons and protons is called atomic weight. Some nuclei are found to be unstable, especially elements with an atomic number of more than 82. To stabilize the nucleus, a few particles leave the nucleus. This process of conversion of radioactive elements into another element by decay is known as transmutation. In fact, a British scientist, Ernst Rutherford, first discovered this process. Rutherford's discovery gave a new direction to modern science. Rutherford was the first scientist who revealed that heavy elements could be converted into lighter elements. In 1908, he was awarded the Nobel Prize in Chemistry for his work. Rutherford found out that radioactive elements emanate radiations, which is in the form of alpha particles, beta particles, and gamma rays. Alpha particles are the nuclei of the atoms of helium that have 2 protons and 2 neutrons. They are of a large mass and move slowly. That is why a thick layer of wind or a strip of paper can obstruct its path. They are positively charged particles. Polonium, with the atomic weight of 214 and atomic number of 84, emits alpha particles and becomes lead. In this way, uranium, with the atomic weight of 238 and atomic number of 92, emits alpha particles and becomes thorium. This emission of helium nuclei is known as decay. Beta particles are negatively charged particles or electrons. In comparison to alpha particles, they move faster. When it emits a beta particle, its movement can be easily obstructed by an aluminium foil. In beta decay, a neutron of a nucleus transforms into a proton and an electron. The electron gets emitted in the form of beta rays and the proton remains in the nucleus. Due to this, the number of neutrons in the nucleus is reduced by 1 and the number of protons are increased by 1. In this way, the atomic weight that is made up of total number of neutrons and protons remains the same, but the atomic number, which is the number of protons, increases by 1. Like, the atomic weight of thorium is 234 and its atomic number is 90. When it gets converted into protactinium, its atomic number becomes 91. Gamma rays are like the rays of visible light. Neither atomic weight nor atomic number changes by their emission. They have no charge and they are capable of penetrating a very thick material. That is why they are more dangerous. Uranium-235 gets converted into thorium-231, thorium-231 into protactinium-231, protactinium-231 transforms into actinium-227 and then actinium-227 into thorium-227. Thorium-227 gets converted into radium-223, radium-223 into radon, radon into polonium and then polonium into lead-211, lead-211 into bismuth, bismuth into thallium and then it gets converted into lead-207. After getting converted into lead-207, the nucleus of lead becomes stable. Rutherford laid the foundation of nuclear physics by discovering the alpha particles and the new atomic structure. Rutherford refuted the old theory of the inner structure of an atom and developed a new model. Before the model of Rutherford, the prevailing theory about the inner structure of an atom was plum pudding model of J.J. Thomson. Thomson imagined that the positive charge is spread in the whole atom and the electrons are arranged into it like nuts and raisins in a cake. Rutherford's assistants, Hans Geiger and Ernest Marsden, conducted the famous gold foil experiment. They selected a radioactive element that produced a beam of positively charged alpha particles. That beam was then made incident on the round fluorescent screen. The moment the beam of alpha particles collided with the screen began to glow. Now, they placed a thin gold foil in between the beam of the particles. They found that most of the particles passed through the foil undeflected, while a few particles bombarded with the foil also got deflected. Rutherford was surprised to see that a few particles were passing through the foil, while a few got scattered. If he were to observe it according to the model of J.J. Thomson, then positive particles should collide and then get scattered. But a few particles were passing through the foil easily. Then he realized that there is a positive charged heavy core in the center of the atom, due to which a few particles were scattering. Rutherford presented a new model of an atom that had positively charged nucleus in the center of the atom. The nucleus consisted of protons and the electrons were revolving around the nucleus in their orbits, like the planets in a solar system. The discovery of radioactivity introduced a new chapter in the study of physics. which have varied applications in nuclear physics, nuclear medicine, agriculture, industry, energy, food processing, and many other fields. For more than 40 years after the discovery of radioactivity, only natural radioactivity was known. In 1935, the daughter of Marie, Irene Curie, and her husband Frederick Joliot added new discoveries in the history of radioactivity. They made the elements artificially radioactive, which is known as artificial radioactivity. After the discovery of radioactivity, first, it was used in the treatment of serious diseases like cancer. Destroying the cells of cancer through ionizing radiation does the treatment. This therapy is known as radiotherapy. In India, a large number of patients are treated through radiotherapy. Besides this, many diseases are identified with the help of radioactive isotopes. There are many institutes in the country where important research and studies are going on in the field of nuclear medicine. Isotopes emitting less powerful alpha particles are used in the tracers. Radioactive tracers are injected in the body of the patient, and then the condition is diagnosed. Due to the radiations, the functioning of the body parts and blood of the patient can be monitored. Radioactive properties of elements are not only used in identifying the diseases, but also used as an important source of energy, like uranium-235. Apart from it, radioactive elements are being used by archaeologists in determining the age of remains of the ancient period. In the upper atmosphere of the Earth, due to cosmic rays, nitrogen is converted into radioactive carbon-14 isotope, which is absorbed by plants and other living creatures. Throughout the life, its number remains stable due to constant decay and absorbing of C14 isotope. But after death, there is no absorbing and the particles decay continuously. And exactly after 5,730 years, its number reduces to half. And this process goes on and on till the end. The specific time of this decay of particles is known as its half-life. Every element has its own half-life. In this way, at any time, we can count the number of particles present in the dead person and estimate its death period. This is called carbon dating. Through the half-life of carbon-14, we can determine the age of fossils. In this way, on the basis of carbon dating, we are able to calculate the correct age of the Earth and the period of existence of ancient civilizations. It is really surprising to see that a single discovery could lead to so many important possibilities. That discovery will prove so beneficial, even Becquerel might not have thought of it. In fact, radioactivity has generated benefits that extend far beyond the original research, often in completely unexpected ways since its discovery a century ago. Still, there could be many aspects yet to be unfolded. Maybe, in the years to come, some more significant applications of radioactivity will be unveiled. We are not afraid of the alpha ray. A sheet of paper will keep it away. A beta ray needs much more care. Place sheets of metal here and there. And as for the powerful gamma ray, pay careful heed to what we say. Unless you wish to spend weeks in bed, take cover behind thick slabs of lead. Fast neutrons pass through everything. Wax slabs remove their nasty sting. These slow them down, and even a moron knows they can be absorbed by boron. Remember all that we've said, because it's no use remembering when you're dead.
Imagine our universe as an incredible superhighway. Billions and billions of particles undertake epic journeys, making their way through space and time. Of these, one particle proves to be the most determined traveler, the neutrino. It's a particle that knows no borders, zipping through dense stars, enormous galaxies, and other interstellar obstacles. Think of the stories it could tell us, if only we could catch it. But how do you stop a particle that's virtually unstoppable? That's a question of science. It all began with a mathematical theory. The year was 1930, when noted physicist Wolfgang Pauli first suggested what he called a desperate remedy to a puzzling problem. Experiments had found that when an unstable atomic nucleus released an electron, the new energy and momentum didn't match expectations. In order to balance the equation and maintain the law of conservation of energy, Pauli proposed a theoretical particle. This particle had neither negative nor positive charge, and in 1933 was given the name neutrino by noted physicist Enrico Fermi. The neutrino successfully reconciled Pauli's dilemma, but it continued to disturb him. He admitted, "I have done a terrible thing. I have postulated a particle that cannot be detected." But Pauli needn't have been so distressed. It would take a few more decades. But in 1956, Fred Reines and Claude Cohen would finally announce the neutrino's detection. Its difficult detection established its reputation. The neutrino was one of the most elusive particles in the standard model of particle physics. In today's physics, the standard model gives the simplest answer to the question, what is everything made of? It provides 12 basic blocks of matter that make up the entire universe. These blocks interact through 4 forces to create all of matter. You may recognize some of the more famous fundamental particles, like electrons and photons. But lesser-known particles like the neutrino are equally fascinating.
Neutrinos is the odd man out among the fundamental particles. Neutrinos has a peculiar property. It's very shy.
What makes the neutrino so shy? It's because forces like gravity and electromagnetism, which affect you and I so strongly, have no effect on the chargeless and nearly massless neutrino. It neither interacts like electrons or protons to form atoms of matter, nor is it attracted to other heavy bodies. All neutrinos show are weak interactions, so weak that they can't be blocked or captured easily.
Neutrinos, by virtue of not having these electromagnetic interactions, you can kind of say, yes, these are clean, they are, all contamination of electromagnetic interactions is removed, and what you can study are other interactions which are weaker than electromagnetic interactions.
It's these weak interactions that give scientists the strongest desire to study neutrinos. Having virtually no obstacles in their path, neutrinos travel, most literally, across space and time to reach us. Primordial neutrinos that were born after the Big Bang still roam our present-day universe. And neutrinos generated by nuclear fusion in the solar core wash all over us here on Earth. In fact, hold up your thumbnail. Now imagine nearly 65 billion neutrinos penetrating it every second. Could it be that some of these neutrinos are coming from the sun? Could it be that some others are nearly as old as the beginning of the universe itself? How can we better understand these exotic cosmic wanderers? Many scientists across the world have chased the elusive neutrino over the last century. India has a distinguished history in this quest, going way back to the 1960s, within the caverns of the Kolar goldfields in Karnataka.
Indians are pioneers in neutrino research. the first ever cosmic ray produced neutrinos was detected at Kolar Gold Field in a neutrino detector 2.3 km underground in 1965. And today, atmospheric neutrinos is a rich field of research by its own right.
In the 1990s, India's neutrino program hit a roadblock with the shutdown of the Kolar Gold Fields. With the demise of this neutrino program, other countries like USA and Japan forged ahead, making new and path-breaking discoveries. It seemed as if the Indian quest for neutrinos had reached a dead end.
Unfortunately, we did not continue this. If we had continued, we would have been on the top of the world. Now, can we recover this lost initiative? We should, right? We should. We can and we must.
This was done in 2000, in January 2000. In this institute, in IMSC, there was a workshop in high energy physics. And during this workshop, many people came together and we said, let's get together and write up what kind of physics we can actually achieve by putting up a neutrino lab in India. And that was actually the first document that we wrote up.
This is the site for one of India's most ambitious mega science projects, the India-based Neutrino Observatory or INO at Theni in Tamil Nadu's Bodhi Hills. What makes this site ideal for tracking neutrinos?
We need at least kilometer depth for our physics requirement. Then we need the rock quality to be good for safety. We need the environmental impact to be the least because we are going to be near forests. And so this whole combination of requirements was listed in trying to find a suitable site for INO.
Today, it's an empty landscape, but within the next 5 years, this will be home to a path-breaking experiment in neutrino physics. The INO brings together the largest collaboration in Indian science so far. This includes 26 leading science institutions and over 100 scientists who are partnering with some of India's top industries. The collaboration is led by the Tata Institute of Fundamental Research or TIFR at Mumbai. The INO project will dig a 2-kilometer tunnel leading directly below a 1,300 tall rock mountain to build a unique underground laboratory.
We are standing on INO land. This is about 26.5 hectares. Here, where we are standing, is where the surface facilities will come. The tunnel itself will start from the cement slab there, that is the marker for the beginning of the tunnel. And the tunnel from there will proceed like this, and you can see this white marker here is the next marker after that, and like that you have the markers all along. And the tunnel will go underneath this mountain and stop below the peak. The peak there, and underneath that it will stop, and that is about 2 kilometers of tunnel. And right below the peak, you have the laboratories at the end of this 2-kilometer tunnel.
As cosmic rays pass through the sheer rock, most unwanted particles will get filtered out. The neutrinos will pass through effortlessly and enter the INO cavern. The biggest of the INO's 3 caverns will house the largest neutrino detector in the world, the iron calorimeter or the iCal. When completed, the iCal will be a massive sandwich of magnetized iron and detector plates. Here's how it'll work. Chargeless neutrinos will pass through an immense magnetic field and transform into charged particles known as muons. Depending on the muon charge, they will bend inside the powerful magnetic field. The charged muons will now trace a curved pathway of electrical signals. 30,000 highly sensitive detectors called resistive plate chambers or RPCs arranged in 150 layers will pick up the signals. 3.6 million electronics channels will carry the data to computer systems. This is the heart of the experiment that will study the properties of the neutrinos, continuing the arduous scientific quest that Wolfgang Pauli began in 1930. It has never been easy or quick to crack the secrets of the neutrino. In the 1930s, Pauli and others like Fermi suggested it was chargeless and massless. By the early 1970s, scientists had shown that neutrinos existed as 3 different types or flavors. These were called electron, muon, and tau neutrinos, and they found a firm place in the standard model of particle physics. What did it imply? That would take a few more decades of experiments, including one of the longest-running experiments in the history of particle physics. From 1970 to 1994, experimentalist Raymond Davis measured the number of neutrinos coming from the Sun. But each time, his experiment only detected 1/3 the predicted number. If both mathematical prediction and experiment were correct, where were the missing 2/3 neutrinos? Then, in 1998, Japan's Super Kamiokande Observatory made a stunning discovery. Neutrinos were not zero mass. The experiment also confirmed that neutrinos undergo a phenomenon called flavor oscillations. This meant that even if a neutrino is born as an electron neutrino, by the time it's measured by scientists, it could, quite unpredictably, change into a muon or tau neutrino. Flavor oscillation and the discovery of neutrino mass also shows us why Raymond Davis's experiment showed just 1/3 the expected number of solar neutrinos.
Neutrino physics has thrown up 2 surprises. One is that you cannot tell the mass of any of these particles. I mean, that is the first most amazing thing. Okay? The reason this happens is because these neutrinos, even though they are produced in these interactions, for example, I said electron type neutrino is produced in the fusion process in the Sun. But the moment it is produced, and as it starts moving and propagating and reaching the Earth, it doesn't look like an electron neutrino anymore. Instead, it is a mixture of 3 other neutrinos, which with great originality physicists called nu1, nu2 and nu3. Okay? So, instead of saying nu e, nu mu or nu tau, you have equivalently mixtures of them which are called nu1, nu2 and nu3. Nu1, nu2, nu3 have specific masses.
The 1998 discovery showed just how unpredictable neutrinos can be. As they travel, they change types and therefore masses. Depending on how nu1, nu2 and nu3 mix, neutrinos appear as electron, muon or tau neutrinos, each with different masses. But this staggering new knowledge threw up new questions. What are these 3 masses? Which one is heavier? Which one lighter? And if the neutrino is no longer considered massless, how does it fit into the standard model of particle physics?
You have to now find a new model which will incorporate all these new features or properties of the neutrinos. Then intuition doesn't help you because there is no intuition about something new. Then you can ask this question, so what will happen, so you have some models which use certain symmetry principles which will say M2 is heavier than M3. Some other models will tell you no, M3 is heavier than M2. And ultimately it turns out that unless you do the experiment, you're never going to settle this.
That's where the INOS iCal detector comes in. The iron calorimeter or iCal is a record-breaking detector. When completed, it will be a stack of magnetized iron 50 meters in length, 15 meters in width, and 15 meters in height, rising as high as a 5-story building underground. This neutrino detector isn't just a first for India. It will also host the largest magnet in the world at 50 kilotons and 1.3 Tesla.
This would be the biggest magnet in the world. There's a challenge in making the coils, and we just haven't built such things. So this is a big challenge. But I think there's a challenge that the engineers know how to deal with, and it will be challenging, but they can do it.
At Kolkata's Variable Energy Cyclotron Center, or VECC, one can get a sneak preview of the future.
This particular setup is the first prototype of the iron calorimeter, which is going to be built in Theni. We would like to test, like in the main detector, that when cosmic muons they come, so they should pass through a magnetic field. When they pass through a magnetic field which you have created in this middle, they should pass through the detectors which will be installed in the main iCal. So, the main aim in nutshell is to have a small prototype of the main detector and magnet, so that we know how to control the magnet, how the magnetic field look like, how the detectors work for days together under this condition. These layers, like 143 layers you will have. So, the total weight, that is mainly of magnet, mainly of iron, is 51 kiloton. So, in that sense you think about now that 51 kiloton of iron has to be magnetized fully.
Other neutrino detectors around the world use materials like water or heavy water for detection. Then why does the iCal require so much iron? Iron is 8 times denser than water. This means it provides more particles as obstacles in the path of the weakly interacting neutrino.
What you need for neutrino detector is a huge mass, 50 kiloton, 100 kiloton mass, and if you put them and then when neutrinos goes through them, some of them may interact. So, that is why the neutrino detectors are always very large.
And why are we building such a massive detector? Because it will not interact unless you put a really huge detector in its way, so that it can interact with at least some of the time. At the end of this massive detector, per day we expect to see 3 neutrino events.
By now, it's obvious. The particle may be minuscule, but its detection requires mammoth instruments. Even so, scientists only expect 3 neutrino detections per day once the INO is commissioned. Needless to say, if neutrino events are that rare, the detectors had better be extremely sensitive. Particle detectors called resistive plate chambers, or RPCs, have taken years to perfect at both VECC and TIFR.
What is happening here? We are developing these RPCs for the INO laboratory. However, we are developing it from scratch. So, we are trying to understand their performances and then optimizing their design so that nothing will fail there.
These fail-safe RPCs are constructed by placing 2 glass plates parallel to each other. A small gas-filled gap separates the two. The outer surfaces of the glass plates are coated with a conductive coating, and a high electric field is applied across the electrodes. When a charged particle, like a muon, passes through the electric field, it creates more charged particles in the gas. This results in an electron avalanche. In other words, a relatively small electric signal is amplified large enough to be read out through electronic circuits. But RPCs aren't designed only for sensitivity to tiny charged particles. They're also designed for longevity.
The iCal experiment is expected to run something like 15 to 20 years. So, it is very important not only that we want to make these RPCs successfully and characterize them and make sure that it indeed satisfies the criteria that is required for the iCal experiment. We also want to make sure that they run for as long as the iCal experiment wants to run. And iCal requires 30,000 glass resistive plate chambers, the active detectors that the iCal is going to use. And that is indeed a big proposition, because nowhere in the world at the moment there is such a large scale deployment of glass resistive plate chambers.
If you think that the INO's team can rest easy once they've cracked the RPCs, think again. The INO needs a strong network of sophisticated electronics to read out the detector's data.
You may have very good detectors, but without this system they are like blind. We cannot read data from them. Okay. So, we need these electronics to get whatever sensitive information we are getting from the RPCs to be recorded and to be analyzed later on. basically that if this doesn't work good, then we don't have a good detector.
Every small piece of indigenously developed electronics signifies a giant leap forward in Indian engineering.
We can say that we are going from here to building a new kind of high energy physics electronics that is comparable to anywhere in the world.
As of 2013, many components of the INO's detector, magnet, and electronics have entered an intensive testing phase.
This is our online monitoring system. Actually, as and when the cosmic ray particles are going through our detector, it's getting detected and immediately it gets displayed here. And not only that, of course, these are cosmic ray muons. We will be using these muons also to study certain physics. So, while this is the purpose of this setup is mainly for R&D, but at the end of it, we will also get some physics out of it.
What are the immediate physics goals of the iCal experiment of the INO? It's to investigate neutrino flavors and their oscillations in order to learn more about their masses. This is especially critical in light of the recent detection of the famed God particle or the Higgs boson. So far, the Higgs boson has been the linchpin in the standard model of particle physics that gives all other fundamental particles their mass. All particles, that is, except the neutrino.
Higgs cannot give mass to the neutrinos. So, since experimentalists now have discovered the neutrinos have got mass, you see we are now able to take fundamental physics many steps above even the Higgs boson, because it will tell us what is the window beyond Higgs boson.
The neutrino's mass could also open up a different kind of window, one that shows us the future of the universe.
They change the mass balance of the universe, they change the density of the universe. Okay? So they will change also the way the universe evolves, because we know our universe is accelerating, and whether our universe expands forever into what is called a cold death or recontracts back into a second Big Bang will depend on the current density and what is the critical density at which whether it will keep radiating outwards or whether it will close back on itself. Now by adding massive neutrinos, you are changing the whole dynamics and our understanding of how our universe will evolve in the future.
With the INO, India can take a front row seat in global high energy physics, and not just scientifically.
So, INO has this twin project, twin aim, namely not only to discover more things about neutrinos, but also to enthuse students, so that we will create an army of young scientists who will be trained to do fundamental research at the cutting edge.
It's not only just the neutrino physicists that will be participating. You need a well qualified engineers who can build your magnet. You need electronic specialists who can build your chips, data acquisition system, the software gurus who can design the software for monitoring, etc. So all these different kinds of people have to put together. This is a collaborative nature. We have probably, this is the first time such a large collaborative effort is taking place.
It turns out this collaboration is already inspiring a new spirit within the Indian science community.
We find it difficult to collaborate with other people. Of course, we do that with in foreign labs, but doing it among ourselves is going to be a challenge. But I think it's a challenge that we will learn from. We will overcome it, and we will learn how to cooperate with each other. And that will, hopefully this will set an example for other collaborations, big collaborations in India.
A big part of this collaboration is community itself. Local residents around the INO site in Theni are given all the information to dispel baseless fears and misconceptions.
General outreach happened with the public and with concerned environmental activists. Talk to the villagers, just telling them about what will be the impact of the project on them, and also some science. So we have always highlighted the fact that the primary gain from having INO in their site is that they are going to have an educational institution near them. And we have talked to the students in the locality, talking about what kind of opportunities they can have to do research with us. We welcome groups to actually associate with us. For example, American College in Madurai is one of our collaborating members.
Periodically, we go there, we have science, mela and things like that. Whenever there is an opportunity, our scientists go and explain to them what we are doing, and that has created a very positive, atmosphere. among the local people now about this project.
When completed, the INO will become a hub for particle physicists from all corners of the globe, drawn to the secrets of the odd neutrino. What stories will it tell us? How will it change the way we view our universe? What will it tell us about our past and future? Curious about the answers? Watch this space. If you'd like to share your feedback on today's program, please send your suggestions and comments to Vigyan Prasar, C24 Qutub Institutional Area, New Delhi 110016, or you can mail us at info@vigyanprasar.gov.in. Twisting and blowing through our world, making the seasons move and the landscapes change form. The wind and its restless gusts are nature's movers and shakers. Without wind, plants wouldn't spread their seeds so efficiently. Birds and insects would find it difficult to fly. Boats would have to lower their sails, relying only on paddles to make speed. And aircrafts, gliders and balloons wouldn't be able to glide across the skies. Most importantly, without wind, we would lose an important piece of our energy-secure future.